Alright class, today we're going to look at uniform acceleration, and hopefully your test went well on kinematics, some intro stuff on speed, velocity, distance, displacement, and acceleration. Today we're going to look at more problems that are usually multi-step problems, but we're going to derive 3 new equations today. They're going to help you solve those a lot easier than what they would be if you were doing them as multi-step. So let's kind of go through this sheet here. Again, earlier we looked at acceleration. It's just the rate at which a velocity changes with respect to time. So we said that either the speed or the direction could change, and if that happened, we would then accelerate. So we get an acceleration. So let's look at this example problem. We have an initial velocity of 0 meters per second, so it starts from rest, and it accelerates in a straight line at a rate of 2 meters per second squared. So that's the acceleration. We can see that after 1 second, the object's velocity would then be 2 meters per second. And we've kind of talked about this already. So after 2 seconds, how fast is it moving? Well, if it's accelerating at 2 meters per second squared, that means it's increasing its velocity is changing 2 meters per second every 1 second. So 1 second later, it's now going 2 meters per second faster, so it's going at 4. Another second later, it's going another 2 meters per second faster, so it's now at 6 meters per second. And another second later, we're now moving at 8 meters per second. So let's look at the graph here. So if you notice, here's our time interval, and this is our velocity each of those different times. And what do you notice about that if we're taking snapshots every 1 second? What do you notice about his distance between each successive second? You should notice that the displacement is then increasing, because again his velocity is increasing, and therefore the distance that he runs during that 1 second interval will increase. So let's look at objects that move with a uniform acceleration. Uniform just means a constant acceleration, so it's the same acceleration throughout. So we're given an example here. I'll let you read that. Now, I'm going to kind of go away from the PowerPoint here and go to show you how I would solve these next problems. Okay, so let's look at step 1. It says, if you notice, we have an initial velocity, we have a time, and we have a final velocity for the object. And we should be able to see, and we want to know what? We want to determine the displacement traveled. Well, again, we should be able to see that the object's average velocity during those 3 seconds was what? Well, if we look in, if you remember what an average is, we take the final velocity plus the initial velocity and divide by 2. So if I plug this in, the final velocity was 40.0 meters per second. The initial velocity was 10.0 meters per second divided by 2. Again, if I'm showing my addition rule, I can show it just above, and again, I'm good to the tenths, so my answer is 50.0 meters per second. Divide by 2, and I get a value of 25.0 meters per second as the average. If we then take that average velocity during the 3 seconds, how far did it go? Well, essentially, if this is the average, we can assume that this is the velocity the entire time. So instead of actually accelerating from 10 to 40, we could treat it as just driving or moving at that velocity the entire 3 seconds. So it's essentially traveling 25.0 meters per second for 3 seconds. So using our equation here that the average velocity is the displacement over the total time, we can solve for displacement. It's just velocity times time, and therefore we get 25.0 meters per second times 3.0 seconds for a grand total of 75 meters. Again, 3 digits, 2 digits, the answer has 2 digits. Now, let's make it easier. We could solve this in 1 step, and we do that by using some algebra, and that's what we're going to do here to solve these 2 equations. If you notice, this is an equation for average velocity, and so is this one up here. So why not set these two equations equal to each other? Well, we can do that, and that's what it's showing right here. We can say that this equation is equal to this. So let's solve this for D. How would we do that? Well, it's D divided by T, so I'm going to multiply both sides by T. I'm going to rewrite this so it's a little bit easier to see. So let's solve for D. D is equal to VF plus VO, that quantity times T, all over 2. So let's substitute and solve now. What was our final velocity? 40.0 meters per second. Initial velocity was 10.0 meters per second. Time was 3.0 seconds. And we divide that by 2. So again, when I solve this in my calculator, I can show my addition rule right here. 50 times 3 divided by 2. Most of us can do that in our head. 50 times 3 is 150. Divided by 2 gives me a displacement of 75 meters. So again, we get the same answer, but we did this in one step using our new equation right here. Okay? Let's look at the second example. So now we have an initial velocity, we're given an acceleration, we're given a time, and we want to determine displacement. So what are we not given? Well, we're not given the final velocity. It's unknown, as well as the displacement. So how can we find what the final velocity would be? Using this equation, which we've learned at this point, so that's our acceleration, change of velocity over time. Solve for VF. So let's do it. VF equals 5.00 meters per second squared times T, 3.00 seconds, plus the initial velocity, which was 10.0 meters per second. I'm going to give you a second. If you want to, pause the video and solve this, and then you can start the video again and you'll see the answer. Okay, here's the answer when you solve it out. Multiply the A times T, and to get this value, again, 3 digits, answer has 3, but I'm going to use it in a calculation, so I carry an extra digit and underline it. Show my addition rule, I'm good to the 10th, good to the 10th, answer's good to the 10th. There's my VF. Okay, now that I've solved for the final velocity, I can then solve for the average velocity using the equation that we used earlier. Average velocity is just the sum of the two and divided by 2. So again, work that out and click pause, work it out, and then hit play. Again, here's the answer to that work. You can see here, here's our final velocity, here's our initial velocity. Carried an extra digit and underlined it because we're using a calculation in a calculation. Showed the addition rule, 10th, answer good to the 10th. Carry an extra digit, divide by 2, so we get an answer to 3 digits here, 17.5 meters per second. Now let's move on here. Now if we know the average velocity and the time, again the time was given to us that it's 3.00 seconds, we then can find the distance that was traveled. So I'll give you a minute to do that. Pause the video. Again, here's the solved problem. Again, you can see that we carried an extra digit and underlined it from there to there. 3 seconds was our time, and we get 52.5 meters. And again, instead of doing this in 3 steps, we can derive this equation and do it in 1 step. So let's see how we derive this equation. We actually use the 3 equations that we've done. So if I say, for example, D equals V naught, or I'm sorry, average velocity times time. What is average velocity also equal to? Well, it's equal to this up here. So we can substitute that in for this average velocity and get this equation. Look familiar? This is the same equation that we derived earlier, back here. See it? It's right there. Now what is our other unknown that we don't know here? Our other unknown is the VF, the final velocity. So do we have an equation that solves for VF? Sure we do. It's right here. So I'm going to take this equation and I'm going to substitute it in for the VF in my equation over here. Pause and then try that on your own and see if you get what I get. Okay, so let's take a look. If you look in my VF position, again I said VF is equal to AT plus VO. So I took that right there and I plugged it in right to the VF. And you can see that right here. There's the AT plus V naught. And then I have another plus V naught, which is this guy. And that whole quantity is multiplied by T. So you can see how that's done right there. And then all of that is divided by 2. I guess this division should be kind of throughout. Okay? Now let's simplify. What is AT plus V naught plus V naught? That looks to me like AT plus 2 V naught. Again, that's times T all over 2. Let's simplify even more. Let's multiply the T throughout. So now we have D is equal to AT squared plus 2 V naught T all over 2. So all I did is I distributed the T to there and to there. And now I'm going to move and I'm going to make these individual fractions. So this is like a 1 here, so 1 divided by 2 would be 1/2 AT squared. And then 2 divided by 2, they cancel, so I get a V naught T. If you notice, that is the equation that I have here. D is 1/2 AT squared plus V naught T. And now I can substitute all of my values in here. My acceleration for this particular problem was given at 5.00 meters per second squared. I had a time of 3.00 seconds, which I have to square that value, plus, I'm running out of room here, V initial was 10.0 meters per second, and I have to multiply that by the time, 3.00 seconds. And this isn't very good, that should be right in there. Didn't leave myself enough room. Should have started way over here. But if I then solve that, I'm going to get the same distance of 52.5 meters. So you can try that out, see if you get that particular answer in your calculator. Okay, this last one is just like the bonus that was on the test. It gives you an initial velocity, a final velocity, and an acceleration. And it wants to know how far did the object travel, distance-wise or displacement-wise. So again, let's see if you can go through the individual steps, 1, 2, and 3 on your own, and then you can pause and check how you did once you go through all 3. Alright, take a look and see if you did okay. Again, solving for average velocity, should be nothing new there. Solving for time, nothing new there. And then we can solve for the displacement, taking the average velocity times the time to solve for that. Now we're going to derive the single equation here to get that. So I'm going to kind of help you through it. You'll need to pause at certain points so you can do some of the work. But here we go. The first equation, if you notice, we're not given time and we're not given the final velocity. I'm sorry, we're not given the time and we're not given the displacement. So we're going to solve a couple equations in terms of t. So here's one of them. So t is equal to Vf minus Vo all over A. And we also know another equation that we have. If we look back here to the previous page, we have this equation here, and I'm going to have you solve that for t as you pause. Okay, you should have gotten this equation right here. Again, if you cross multiply and divide, this is what you get. Now we're going to set these two equations equal to each other. And then I want you to see if you can come up with this equation right here. Here's what happens when you set the two equations equal to each other, and then we're going to cross multiply and see if you can do that. Here's my next step after cross multiplying. Now we need to do the FOIL method, the first, outer, inner, last, to get this simplified. Here's what you get after you do the FOIL method, and then these cancel, and if you notice, you're left with the equation that's given. so it works out.